If you take the image enhancement, what is the principal objective of image enhancement? Generally, the objective of image enhancement is to process an image so that the resultant image should be more suitable for a specific application purpose than that of the original image. We will be having a original image, and we will apply an enhancement technique for that. And at the output side of that one, we will be getting an enhanced image. So that enhanced image should be more suitable for a specific application purpose. Here, the important thing is specific application. What type of application we are using, that is dependent on that. See, we are having medical applications. For example, if you take the X-ray image or MRI scanning image like that. So if you want to enhance that image, we will be using some types of techniques. And if you are having some satellite images, otherwise we will be having some whatever consumer electronics like television images like that. For that, we will be having some types of image enhancement techniques. Like that, here the specific application is important. Specific application, whatever you are having, that is important. And enhancement methods are application specific and are developed empirically. As already I told you, here based on the application, we will be empirically design the image enhancement technique. See, if you take the image enhancement, that produces an image that looks subjectively better than that of the original image. That means here on the pixels of the image that will perform. Image enhancement will be performed. We know very well, if you take any image, what is an image? Image is a two-dimensional function that has a measure of some characteristics such as brightness, intensity levels like that. It is nothing but a two-dimensional signal. It consists of a simple matrix of intensity values ranges from 0 to 255. Here 0 represents the black color, whereas the 255 indicates the whatever the white color. Here I am talking about the grayscale image. And between these, we are having 256 whatever levels, intensity levels we will be having. So modification of those intensity levels is nothing but the image enhancement. Simply we are modifying the intensity levels of the image. That's it. We are not doing anything else that. Here image enhancement, whatever we are having, that emphasis specific image features such as contrast, brightness, or suppressing the noise, sharpening or smoothing, whatever. Based on that, whatever the specific feature, here the enhancement method will work. Here, image enhancement methods are fall into two broad categories: spatial domain methods and frequency domain methods. Spatial domain methods, if you take, in this whatever the plane image we are having, on that plane image only it will work. Directly on the plane image, whatever the enhancement methods we are having, that will work. Directly, this will process the intensity values of the image plane. Whereas if you take the frequency domain, in the frequency domain, what we will do is first, whatever the spatial information, spatial intensity values we are having, those will be converted into a frequency domain. And in the frequency domain, in the coefficients of the frequency components, we will be operating. We will be applying some filtering techniques like that. And after that, again, we will reconvert that frequency coefficients into spatial domain and reconstruct the whatever the image. Like that, it will work. That means spatial domain methods directly operates on the image plane itself. And the intensity values itself directly it operates. Whereas frequency domain that operates on the frequency coefficients of the intensity values. After converting the spatial information into frequency domain, and there some filtering techniques, some frequency domain methods we will apply and reconvert that one into spatial domain. Like that, the frequency domain will work. See here, this is the whatever image processing based on that spatial domain. See here, f of x comma y is the image. This is the input image or original image, whatever we are having. And g of x comma y is the enhanced image. This t stands for the transformation function. Here, transformation in the sense we can take the linear or non-linear functions, whatever we are having. That means whatever negative, image negative or inverse transform, thresholding, exponential transform. So all those type of techniques here we will be applying on the image in spatial domain. And whereas in the frequency domain, if you take, see here, as already told you, in the first we convert that spatial information to frequency, and then we will operate that. We will apply the filter. Here we are using the convolution principle. That means convolution in time domain is equal to multiplication in frequency domain. Based on that concept, here the frequency domain, whatever methods will work. Okay, here I am not concentrating on this. Why? Because my focus is on histogram equalization and related to that histogram equalization methods. That's why directly I am jumping into that topic. Before going to that, what is a histogram? See, here we are having an image. If you take an original image, here I am taking, and simply I am using these commands. That is, I am reading the image and I am using the command I am image hist of I, so that it generates this. So what we can understand from this? From histogram, what we can analyze? What we can take the features of the image. See, here histogram, whatever we are considering, that is the graphical representation of intensity values distribution. As already I told you, whatever the image we are having, that image consists of m by n number of intensities, where m stands for rows and n stands for columns. So it is a matrix. So whatever the intensity values we are having, so how those intensity values are distributed, that can be explained pictorially, graphically, by using this histogram. That means how many pixels are there with the intensity value, that it can represent. For example, here on the x-axis, if you can consider, on the x-axis of this image, I am taking whatever the intensity levels starting from 0 to 255, whereas 0 stands for pure black and 255 stands for pure white. And in between this, the intensity values are distributed. You can observe this. Here we can have one point here. Here, most of the intensity values in the image are restricted towards the lower region only, not in the upper region. You can consider it here. Here you can observe here. So here, this is a problem we can have. So if you want to increase the contrast of an image, whatever the intensity levels we are having, those intensity levels should be distributed uniformly in all regions. It should not confine to a certain region. It should be distributed. So if you would observe this figure B, this is the equalized image. Of course, we can take that one as histogram equalized image. After the equalization, whatever you can apply, you will get like this. Subjectively, you can analyze. This is somewhat information is losing here, and here we are getting some information. We are going to observe some information here, and this is the histogram of the processed image or the enhanced image. Observe here. Here, whatever the intensity values we are having, they are distributed. They are stretched. Whatever the intensity histogram equalization we are having, after doing that operation, whatever intensities are stretched during the entire length of the intensity range. So that is about that. That is the histogram. Here, whatever the image enhancement methods based on histograms, these are the different types of methods we are having. Histogram equalization, brightness preserving. So of course, we can read these things. My interest is brightness preserving dynamic histogram equalization. We are having these many techniques, but my interest is brightness preserving dynamic histogram equalization. Here, today, I am going to explain about this one. Before that, briefly, we can have all these things. In brief, we can have. See, whatever the histogram equalization we are having, what it will do, histogram equalization, it is a processing technique and it is used to improve the contrast of an image. As already told you, it increases the contrast of an image, and it accomplishes this by effectively spreading out the most frequent intensities. Whatever the intensity values we are having, those will be stretched out in the entire range of the intensity values. As already I told you, intensity value 0 to 255. So it will stretch the histogram equalization technique. It will stretch most of the frequency values throughout the intensity range of the image, whatever happens. So here, whatever you can observe this one, I am going to this. This is the source image or input image we are having. So after histogram equalization, we got this equation. We got this image. Sorry, we got this image. You can subjectively you can see. So which one is better? The equalized image is better compared to the source image. And corresponding to these two images, whatever the histograms we can observe, for the before the enhancement, whatever the histogram we are having, you can observe a peak here. That means most number of the whatever the intensities of the pixels that is concentrated in this region. Okay, so of course, if you can observe here in this from 0 to 50, there are no intensities present. No intensities are present from 0 to 50, and afterwards, here only we will be having. After equalizing this, after applying the histogram equalization, you can observe throughout the entire region from 0 to 256 levels, we have stretched the intensity values so that you will get like this. And of course, so subjectively, I told like this. What is the mathematical operation behind this histogram equalization? That we can see here. See, if you take the f of I comma j as input image, and it is having the MR by MC matrix, as already told you, image is a matrix of integer pixels ranging from 0 to L minus 1. Here L is nothing but 256 here. And here we are first we will calculate the Pn value. Pn, where Pn is equal to number of pixels with intensity n by total number of pixels. For example, take 50, n is equal to 50, I can take. That means the level, intensity level of 50 I am taking here. So P50 is equal to number of pixels. In that image, how many pixels are there with 50? That you can take in the numerator, and in the denominator, you will be taking the total number of pixels. So that you will get that Pn. So Pn here, whatever the normalized histogram of F, you can take it. And after calculating this one, how the equalization process will be performed in the sense, g of I comma j is equal to floor of L minus 1 summation n equal to 0 to, like this we can have. Here floor command, it will round off the whatever the value to nearest integer value. And this is equivalent to the transformation function. As already told you, whatever the spatial domain techniques that directly operates on the pixels of the image, directly on the image plane, it will operate based on a transformation function. So that transformation function here, it indicates T of K. This equivalent to this G of I comma J, which is the equalized image coefficients. Here I comma J, these are nothing but the coefficients of I equal to 0 comma 0 0 1 1 1 2 1 3, like that we can take. But generally in the matrix 0 0 whatever you won't get, you have to start from 1. But whereas in the intensities, you have to start from the zeros. Okay, so this is the transformation function we can have. So actually each pixel, each intensity value will be calculated based on this transformation function only. A new intensity value will be projected. For example, here if you take the intensity value of 50, after transformation, that value may not be 50. It may be some other thing, some other value. Why? Because the transformation has been made based on the transformation function. Like that, it will work. Each pixel, each intensity value will be mapped here based on this transformation function T of K. Right? Next. Of course, this I discussed here. Of course, this is one more example I told you. See, before equalization, whatever the image we are having, after equalization, whatever we are having, this is the histogram equalization only I am saying. See, before equalization, so much of things are, that is constrained only to a specific region. Whatever the intensities we have taken, see this red color. Only in the specific region only the intensities are distributed. Before this, from 0 to 100, whatever, we are not having any intensities. From 200 to 250, we are not having any intensities. After equalization, we are having equal, whatever some values we will be having. Is it right? From 0 to 250, you can. This is the use of histogram equalization. After that, we can have. Of course, histogram equalization, whatever we are taking, that usually increases the global contrast of an image. Globally, you can, whatever, if you take this image, so this image can be globally enhanced. That means contrast can be enhanced globally. So this leads to some saturation effects in the enhanced image. What do you mean by that saturation effects? In the sense, if you take some regions, for example, if you take this region, this is looking more white than that of the input image, whatever we are having. Actually, it should not be this much of white color. Precisely speaking, whatever the input image, whatever the real image we are having, since we have to preserve the mean brightness of the input image, actually it should not be this much of white color. It should be somewhat lower level intensity value it will be having. But since this histogram equalization is working entire image, on the entire image, some saturation effects will come like this. That means saturation effects in the sense, how we can say in the sense, in the unwanted region, you can have more contrast. In wanted region, you can have less contrast. Unwanted increase of the contrast we can have here. That is nothing but saturation effects. So in order to overcome this problem, we are having different types of technique. Of course, this is also histogram equalization technique, whatever the adaptive histogram equalization. So this differs from the main histogram equalization. This will work on the sections. Some sections of the histogram, it will work. Several histograms, whatever the image we are having, for that image, we will take different sections of the image. For different sections of the image, we will take different histogram equalizations. And finally, we will combine them. So that is the histogram, adaptive histogram equalization. Mainly, We have to concentrate on how histogram equalization works. Why? Because in the later sections we are using that thing directly, right? Next, second method, brightness preserving by histogram equalization. So in order to overcome that problem, whatever saturation effects, that is for consumer electronics like TV, television images, or whatever X-ray image, whatever medical images like that, we cannot get, we should not get that saturation effect. So in order to overcome that, we are going for following equalization techniques. In that, first one is brightness preserving by histogram equalization. This is very simple. Here, whatever the figure I have shown you, this is nothing but the histogram. This is the continuous one I have taken here. Continuous one. I have not taken the bins here continuously. So here we are selecting one threshold value, xt value we are selecting. So here xt is nothing but mean value of the intensities of the image. Otherwise, we can take the average intensity of the all pixels, whatever input image, whatever we are having. For that input image, the average intensity of all pixels we can take. That average is nothing but xt here. For example, 150. 150 is the average. So that point I will take as a threshold. So below that, above that, I have divided into two regions. This histogram has been divided into two parts based on that mean value of the input value, average intensity values of the pixels of the input image. Now I got two subsections, two sections I got here. Two histograms I will take, before xt, after xt. Now I will apply separately histogram equalization for these two parts, and finally I will combine them so that I will get somewhat enhanced image. That is about brightness preserving by histogram equalization. Next, dualistic subhistogram equalization. This is also similar to the bihistogram equalization previous technique, but here the difference is, in the previous one we have calculated the mean, the average value of the intensities of input image we have taken as the xt value, but whereas here we will take the median value you can take. So remaining thing, everything is same. There mean value you calculated and it has been taken as xt. Here you are taking the median value of the input intensities, that is taking as xt, and the remaining thing sections, that means based on that xt you will divide the histogram into two parts, and you will apply separately for two parts that histogram equalization, and finally you will combine them. That is same there, mean, here median. And of course latter one is minimum mean brightness error by histogram equalization. So this is also that is extension of the previous techniques. This difference, what this will do is, whatever the input image mean and the output image mean, whatever the equalize, some sections it will take between 0 to L minus 1, some sections it will take, and it will apply the histogram equalization. After that we will be getting the output image. For input image mean and that equalized images mean, both will be calculated, and the average of those two we will take, and that average we will take as xt, and remaining is same. See here xt is important here. How the xt value is calculated? Mean here median, here whatever the average of the input and the difference between the input and the output mean brightnesses. Next one is recursive mean. This is similar, whatever somewhat different compared to the previous one. Here whatever the subhistograms we are having, those are divided into again subhistograms. See here two subhistograms we are having. Now again this subhistogram will be divided. Next again that subhistogram will be divided. Similarly this side also. Like that it will perform. Like that it will perform. Based on the mean value it will do. Based on the mean value it will do. Just tearing the paper into pieces and pieces. Like that it will work. Of course wherever the R value is large, brightness will be preserved here, whereas it will be difficult. If you take a very large value, it will become more complex for us. And in the similar manner, recursive sub-image histogram equalization also, we will take 2 power R terms. Here R, here 2 power R pieces we will take. Sub-histograms we will take it. Remaining thing is same. In the multi-peak histogram equalization technique, here what we will do is, whatever the up to so far, based on that threshold value, we have divided the histogram. Xt value, we have divided the histogram. But based on the local maximas, we will be dividing the histogram. Local maximas. Based on the local maximas, here we will be dividing the histogram. What do you mean by that local maximums and all those things? In the sense we can observe here in this figure, we can observe Here, whatever the here, observe here, in this region, in this local region, this is the maximum. In this local region, this is the maximum. In this local region, this is the maximum. In this region, this is the maximum. Like that, we will be having the local maximas. Similarly, local minimas also we will be having. This is the local minima. This is the local minima. This is the local minima, whatever. Local minimas also we will be having. Local maximas we will be having. So here, there is difference between local, global. Local means within a certain region, whatever the minima or maxima we can take, whereas the global means during the entire image, during the entire histogram, one global maxima will be there, one global minima will be there. But you can have multiple local minima and multiple local maxima values. Right. Yeah. Sorry. So based on the local maximas, we can divide the histogram, and we will apply separately histogram equalization for all the things and combine them. And whereas dynamic histogram equalization here, same as that of the multi-peak histogram equalization, but whereas here we will depend on local minimas. Local minimas will depend, and based on the local minima, this method will split the histogram into subsections, and for each subsection we will apply the histogram equalization, and finally we will combine. Of course, up to this we can have evaluation, and afterwards this is my interest, whatever brightness preserving dynamic histogram equalization. So here, whatever the consumer electronics we are having, television, all those things, this method is important for those contrast enhancement. Why? Because here the mean brightness of the input image can be preserved. That is the specialty of this method. Mean brightness of the input image can be preserved here. So this method consists of the following steps: smoothing the histogram with the Gaussian filter. Okay, you can read these things. No need to have it. We will come one by one. First step is smoothing the histogram with Gaussian filter. See, whatever the image we are having, in that image, whenever you are capturing that image, otherwise, whenever you are processing that image, at that time, some intensity levels may be missed. So first, we need to fill up those missed intensity levels. So in order to do this one, we are going for smoothing the histogram with the Gaussian filter. So whatever the intensity levels, those are missed. First, what dissipated intensity levels we will fill up with a linear interpolation. Then histogram will be smoothed by using the one-dimensional Gaussian filter. Wherever artifacts are there inside the image, those things can be avoided by using this Gaussian filter. Here, this is the Gaussian filter what we can apply. This is the expression for Gaussian filter what I have used. Here, x is the coordinate related to the center of the kernel, whatever we are taking. If you take a mask, in that mask, whatever the center value, that indicates this x value. We can also call that kernel. And sigma is the standard deviation. Generally, we will take 1.07, something like that. Here, I took in this work, I took 1.07 as sigma value. And after applying this image, we can have a smoothed image histogram. After that, we have to locate the local maximas. As already told you, here after plotting the histogram of smoothed image, we will have like this. Here we have to note down the local maximas, where the local maximas are happening. So for that purpose, here we are following one technique. That means first, whatever the signs of the first derivative of the smooth histogram, first what we have to do here is, whatever the smooth histogram we are having, first derivation we can apply for that. For that histogram, we will apply the derivation. After derivation, we will be getting the signs. So we will locate the local maximas as the points where 4 successive negative signs are followed by the 8 successive positive points. That means here 4 negative successive points followed by the 8 positive signs. That's why here I took local maxima. Similarly for all the things. See, region 1, region 2, region 3, 4, 5, 6, up to 9. Here we can take. Based on the local maxima, I have splitted this image, this histogram into several subsections of the histogram. Sub-histograms I have divided. So afterwards, I will take, I will note them. Let M0, M1, Mn are the n plus 1 gray levels corresponding to local maximums. So here, first sub-histogram, that is ranging from I minima to M0. What do you mean by this in the sense? We have to go here. We have to go for the previous one. See, first of all, 0 to, for example, this level I took 50. This level I took 100. For example, I am taking like this. So first 0 to 50 I have to take. This is one bin. Next 51 to 100, second bin. Next 101 to 150, like that it goes. That is the meaning of this one. Here, whatever I minimum comma m naught. Here m naught, what I told you, there is the first maxima intensity value. Similarly, for the remaining things also, we can take like this. So afterwards, after splitting them, whenever the subhistograms we are having, they cannot assure very good enhancement. Why? Because subhistograms with smaller range will not enhance significantly by the histogram equalization. For that purpose, we have to span them. We have to remap them. We have to increase the range, dynamic range you have to increase for those values. So that can be obtained by using this formula, span I, high I minus y, factor I, like that range. This is the range, final range, whatever I have taken. For example, 0 to 50, what I am taking, that range it indicates. Here, whatever the values here, high I indicates the highest intensity value in the histogram, lowest value Li, and M is the total number of pixels in the range. Afterwards, as usual, from the range 0 to 50, 51 to 100, like whatever the subhistograms we are having, where they are mapped into new dynamic ranges, for all those things, we can apply the histogram equalization. So same, this is the equalization of heat partition independently. So here we will apply the histogram equalization, starting from starting pixels to ending pixel, whatever value, intensity value. So this equation resembles the histogram equalization equation. This is the transformation function what we have applied here. This is similar to histogram equalization what I told you. This we can apply on each sub histogram, and we will map them. And finally, we will whatever the image we are getting, that that you can get the enhanced image, and that enhanced image we have to normalize. Why? Because input image brightness we have to maintain. For that purpose, here we are going for the normalization of the image brightness. Here I am using this function g of x comma y. This is the output image, whatever mi by m naught into f of x comma y. This is the after equalization, after the previous step, f of x comma y will be getting. Here mi stands for input image mean brightness, m naught indicates the output image mean brightness. Based on this, we will we will normalize the image brightness. So g of x is the final output image. Okay, like that we can have. Okay, so here in order to analyze this one qualitative metric we have taken, that is average absolute mean brightness error. So this is given by 1 by n into absolute value of m2 minus m1. Here m2 is nothing but the mean brightness of the output image, and m1 is the mean brightness of the input image. Absolute values we are calculating those means, and here n is the number of images what we are taking. So if you take this one, so subjectively you can analyze. This is the input image, histogram equalized. Of course, whatever the techniques I discussed now so far, so all those techniques here we have implemented. You can observe these things. And here you can observe this is the input image. This is the last method. That is the brightness preserving dynamic histogram equalized image. See here preserving. That is the input mean brightness is preserving here. Of course, contrast is also increased, and the input mean brightness also preserved. You can take these things. So it will become more black. Some portions you are, and here this is the whatever AAMB, that is the whatever the qualitative metric I have taken. For different methods, these are the values. Less value you should have. So for brightness preserving dynamic histogram equalization, we are having less value compared to previous techniques. That's why we can finally say that brightness preserving dynamic histogram equalization can preserve the input brightness by increasing the contrast. It is increasing the contrast, and also it is preserving the mean brightness of the input image. Okay, so this work can be whatever the future scope, we can improve the entropy also. Entropy of the image, that means whatever the entropy is a measure of the degree of randomness in image. So it indicates how much of loss has happened in the input image. So whatever that entropy also we can increase in the future work. So this is about my presentation for today. Thank you.
Thank you,
Sir,
sir.
is that, sir?
Thanks for
Okay.
your. Thank you, sir. Thank you very much.
And of course, we
I'll
can
try to
also
pass
implement this
point.
one for color images also. 1 second, sir. We can implement this one for
Sure.
color images also. Same method. Color images in RGB image means R channel, G channel, B channel will be there. RGB. For each channel separately, we can apply this technique. so that finally you can concatenate all those things, so that you can also implement this one for color images also. Very easy, right? Okay, sir. Thank you, sir.
Okay, sir. Any queries from participants, sir?
Sir, Pawan, sir.
Okay. Sir,
Pawan, sir.
Tell me, sir.
Yeah, so you
Sir, tell me,
focus
sir.
on Instagram. Yeah, yes. You focused on
Yes, sir.
Instagram-based image enhancement. So
Yes, sir. Yes, sir.
there are several techniques with the help of mask, with the help of mask or
Yes, sir.
median
Yes, sir.
filters.
Yes, sir.
There are several
Yes, sir. Yes, sir.
median filters are available to enhance the image enhancement.
Sir.
So
Yes, sir.
how we say that histogram perform better when compared to mask type image enhancement techniques? So,
Sir, here, as already told you, image enhancement is, that is application specific, sir. These methods, histogram equalization based methods, are basically used for whatever consumer electronics, sir. That is the TV images like that. So whatever the median filter, all those methods, we can apply them based on the application specific. Based on the application, we can apply, sir.
yeah, that is the major important. The students, especially if they means the techniques, there are several techniques are available. So
Yes, sir.
which
Yes, sir.
technique
Several
is
techniques are available.
which type of the application domain is the most important?
Yes. Yes, sir. Application
So is
domain.
it
Which
correct,
type of
sir?
application? Yes, sir. Yes, sir. Application.
Okay.
Which type of application we are applying, sir?
Okay. You performed all these with the help of MATLAB, sir?
Yes, sir. MATLAB, sir. Yes, sir. Yes, sir. Yes.
Okay, fine. So, any other participants? Okay, sir. Thank you, sir.
Sir, thank you very much. Thank you.
Okay, sir. Thank you, sir. Thank you very much for your nice presentation.
Okay, sir.
And I thanks all the participants for staying here and listening this session. Okay, with this we stop this today's session. Thank you, sir. Thank you one and all.
Thank you, sir. Okay.